Hello, Mr. Eric, Mr. Ryan, are you alright? Okay. So we have talked about trie before, yeah? A long time ago, trie. This is the prefix tree. Anybody remember we have talked about? Right? So what's trie prefix tree? Okay, I understand you might not remember, but let's review this again. Prefix tree. So if we have a few words, right? We have a few words like Eric, Ryan, Chesley, Pyro. Okay.
We don't have capital.
Okay, Pyro. Okay. So we have a few words,
We don't
right?
have capitals.
That's okay. We have these words, right? And we want to insert it into, and we want to find out, look, if we want to find out if given a word, like you want to search, yeah? You want to search this a word, and then we want to be able to return if this word is in the word. We could use, we could just say word in words, right? But let's going to take on time, right? Because we need to do this linear search to check one by one, right? That's slow. Alternatively, we can do what? We can convert this word and put it in a hash table notebook, right? If we put it in a set, so if we put word equal, if we put it in a set words, right? So all these word is put in the hash set, and then if we set if word in, okay, so let's say this is A, in A. What's the time complexity if we do that? If we convert these words into a set, and then we check if the word in A, what's the time complexity?
OA.
Oh, sorry?
OA.
It's not OA, what's it OA? I'm saying convert it to a hash set. Without the converting, we need to check one by one, that's ON. If we put it in a hash table, what's the lookup time for what's the lookup time for
O1.
O1? Yeah, constant. That's the advantage of using the hash set, yeah? We talked about that, yeah? Okay, so how about if I want to find if a word has a prefix, right? So if I say this is a prefix, it's not exactly the word, right? It could be a prefix. Then the hash set is not working in this case, right? Because then if I search ER, you need to tell me, okay, it's true because ER is the prefix of Eric, right? If you tell me if the prefix is chess, and search prefix will return true because chess is a prefix of Chesley. Yeah, Ryan, make sense? Eric, make sense? Yeah. Okay, yeah, makes sense. So, but in this case, how can we do it? We of course we can do this linear search. Yeah, we can do this and checking it, And by the way, this is not exactly the ON, right? We are assuming to compare two words is O1 constant, but ideally, practically, to compare if the two strings are equal, that's going to take ON time. So it's actually ON squared. Okay, ON squared. Now prefix is the same, right? It's the same. I have to do this check one word, and check if this is the prefix of that, right? Yeah. If you check if it is the prefix of that. So that's going to take ON squared time as well. So how can we do this better using the prefix tree? So look, everything, this is magic, yeah? This is a review. How can we do this? So we build a prefix tree. So we go through this, yeah? We go through this. Let's say, okay, this is the root, yeah? This is a tree, prefix tree. Root, empty here. Then this is empty here. And then, okay, E, I got E. Yeah? I got the R. Look. I got the I. And I got the C. Okay, so yeah, just by appending the letters on the tree, and R, Y, A, N. R, Y, A, N. Okay, so, and the N, when it's terminal nodes, when this word, right, when this node, look, because Eric, this is a word boundary ending here, so I set this additional field to true. to true. Otherwise, all other nodes are false, right? And chastity, again, chastity. So C, yeah, H, E, S, S, L, Y, okay, L, Y, and pyro. Okay, P, Y, R, O, okay. Or let's do another one, maybe. Let's put it like what? Erica, okay? E-R-I-C-A, Erica. So look, E-R-I-C, and I put another A, and then this is also a word. I think it's true. And Ryan, let's say riding, okay? Let's put another word. Okay? So R-Y-A-N, and I put another Y here.
Ryan.
Okay. So how look, this is a previous tree. How does that help? Okay, let's say if I want to look up for a word like maybe chess. If a chess is a prefix of any word here, so I can just do this. Okay, so look, it has a try. See, I go here. H, E, S, S. Okay, fine. Look, it's here. So I can follow the path. So okay, chess is a prefix, right? Easy. How about chair? How about let's ABC? It doesn't have A. Okay, so I know it's not a prefix. Yeah?
Yeah.
Make sense? Another example like chassis.
Chassis.
Okay, so look, C is there,
Can you call it
H
chassis?
is there, E is there, S, S. Okay, but now this one doesn't have Y, so we know the chassis is not part of the original dictionary. Yeah? How cool is that? Right? Yeah? Make sense? So how we possess? Look, we possess these words in the list of words. We put it in the tree, construct the prefix tree, which is called. How do you pronounce this, by the way?
Try.
Try. Okay. Try.
Okay.
Prefix tree. Okay. So the time complexity looked up to check if. Okay. To check if a word is in that, is on, right? N is the number of the character in this, right? Compared to on square, right? Remember previously on square, because look, linear search n times. For each one, in the worst case, you need to compare n times, right? But now this is on, so it's the many. We are improving from ln to on square to on. And the space complexity, the previous one, we haven't used any space, it's O1, right? If we do the brute force search. But now we are using a tree, right? We're building this. So what's the time complexity of building this? It's on square, right? So if each word is n dense, and there are n words, so that's on square. Okay, that's the space complexity, right? And then to insert a word in that, it's easy as well. Look, how do we insert? Look, let's say I want to insert another word like Eric, like, okay, without space. How can we insert this? Okay, E is here, so I don't create it. R, I, C, okay, and then what? Air. It doesn't have air, so I put another note. Air, okay, A, I. Remember, when you finish here, I need to set this field to T, to true. Right? So next time I can just follow it. Look, this is, you can call this like a dictionary tree, right? So we are basically putting the words, yeah? We're putting the words, construct the words here, putting in the tree, right? So, and to search a prefix and search it takes a long time, right? Okay, so this is the try, yeah? We talked about like long time ago, yeah? Long time ago, probably, I don't know, in the first 100 days, yeah? Last year, yeah. How does that help? Look, if we, so now I want to do this. I want to search something. So I want to search if I have a question mark here, means that it can replace any words. So okay, so can you tell me if this exists? E question mark I C. If this exists in a word in this dictionary.
No.
Remember, this is any single word. E something I C. Is it in the dictionary?
Yeah.
Yeah, because E R I C. Okay, exactly. How about C question mark E question mark? Is it in here? C, C question mark here, question mark. No. Okay, so maybe it's no. How about C question mark, question mark, question mark, question mark. C
Yeah.
question mark, question mark, question mark. You got yeah, you got it, yeah. Look, question mark means any single character. Okay. So how can we do this? What's your thought? Obviously, we still need to build we still need to build it, right? Yeah, we still need to build this the dictionary tree. But how can we do this when we meet a question mark? Okay, so let's say when we meet a question mark.
We don't care.
That's good. We don't care. How do we not care?
Because it could be any.
It could be any. Good point. So let's say, look, if a tree, I'm here, right? And if I'm at this letter, and the next letter, this is the dictionary here, right? This is the dictionary. Yeah. This is a tree. Look, it's a tree, right? So here, the next letter is question mark, right? Look, this is, for example, this is A, for example, and the next letter is question mark. So all I want to do is that there are 4 possibilities, right? So I can brute force. I can try each possibilities. Yeah. So look, this is a word like let's take this ERIC for example, right? E something IC, right? So now the first yeah, question mark means any letter. So look, if I try this, E, okay, it matches, but the next one is any number, right? And any characters, right? So let's put another one, maybe EXAB, EQCD, okay? I don't know, EXAB, XAB here.
There's so many things attached to my name.
Yeah. Look, EQCD, okay? Okay, and look. So now I'm here. The next character could be anything. So there are 3 choices, which is QRI, right? It doesn't matter because this one matches any. So it could be this one. So how about if I try Q? Q. Then the next letter I need to start with IC. Now I need to match if these are IC, right? Or I choose here. I need to match this should be IC, or match here should be IC, right? Yeah. So I just brute force all the children, and I can do this depth search. Yeah. I can just do this depth search. Okay. So let's quickly rewrite it. Okay. Make sense? Yeah. Okay. So let's repeat again. This is the letter we are currently at, and the next letter is a question mark, and all I have to do is take the kids of these in a try, in the try, and then brute forcing it. And how can we brute forcing it? Depth search. We do the depth search. Yeah? And then look, E something IC. Then look E. If I try this path, this can match to a single question mark. And all I have to do is follow the path to see if the next few characters matches IC, right? Again, here, I take this route, the next few characters should match IC. And X, the next characters should match IC here, right? Yeah? Okay. So now, let's quickly write the try, okay? How can we write the try? Easy, very easy. Okay, let's review a little bit. Class, normally we define a try in a class, yeah? Try, this is the object. And then define constructor init, init, self, right? So usually you can say self dot, let's say words is a dictionary, right? Dictionary with empty dictionary. And self dot leaf is word. Let's say is word equals false, okay? Okay. Right? Now I have to do this insert. Okay, let's do this insert. And then the rest will be the same. Insert, I want to insert the word in a try, right? Insert the word. So first of all, I get the root. Root equals self. Right? So and then I say for W in word. I go through characters by character in this word. I want to insert. Look, I want to insert this Eric in the. I want to insert this Eric in the try, right? So now currently this is empty. I want to insert Eric. So now I have to check what if W E is not in Lu.word, right? Dot word. Then I have to create a node in it. So Lu.word, right? Lu.word W equals try, right? And then I need to walk through. So now I create a word which is E here. E here. And then I need to walk through that. Lu equals Lu.word W. Right? And then I keep doing this until the end. When we reach the end, ERIC, I need to set this to true. So Lu dot is leaf. Is leaf. Is word equals true. Right? Yeah. So this is the magic, right? This is the magic. If this character, if this character, we haven't got a character for this, then we create it and we put it in the try, right? And we work it. Okay. So Eric, look. So what does this do here? I go through the E. Okay. E is not here, so I create the E. I work through it. Okay. R is not here, so I create the R. Work through it. I create the I, work through it. C, I work through it. And then I set this to true. Okay, so for example, if I have another one, E, R, and B, okay? Okay, E is there, so I just work through it. I don't create it. R is there, I don't create it. A is not there, I create it. And I jump to it. B is not there, B, and I set it to true. Make sense? Yeah? Insert. Let's insert a word into the try. Okay. Time complexity. This is n. If there are n characters in the word, then O(n). Right. The space complexity. We're not talking about space here because the try uses, it's already taking space, right? So there's no additional space in this method. Okay. Okay. Now the next word will be search. If we search it, yeah. If we search easy, yeah. If not in that, then I need to return false, right? Easy. If not in that, I return false. Otherwise, return true, right? And then look, if we search entire word, I can do this. I can say, okay, return Lu dot is leaf, right? Because it has to be its word. It has to be exactly match. But if I search a prefix, look, if I search it with a prefix, then I just need to return true. Make sense? Yeah? So each word is Eric, Ryan, what you doing? Each word, what's each word mean? It means it's node, this node, if there's a word ending here, like ERIC, right? For example, I, the field is each word is false because there's no word, there's no such word ending here, right? But ERIC, there's actually a word ending here, so we set it to true, this field. So search prefix, we return true. But search word, we need to return that rule, the node, is word equals true, okay? Ryan, what did they say? Ryan?
If node is equal true.
Okay, now let's do this DFS search bit, okay? Easy. DFS search bit. It's quite similar. So we just have to define, we have to search, okay? This search, this also have this word, but this word can have a question mark, meaning it could match any character, okay? So now most part is similar, Lu.self, and I go through this for W in word, okay? I go through this is word, okay? Now look, if W equal question mark, okay? Yeah? If this is a question mark, so what do we do? Okay, so let's skip this for a moment. Else, if we know question mark, if what? Else if W not in Lu.word, right? This is the same, yeah? Now we return false, right? Yeah? If it's not a question mark, and if it's not in in the next node, right? Then we return false because it's not matching any prefix, right? Yeah. Now I have to do this root equals. I go to next kit. Yeah. I go to the kit. Root of word w. Okay. And then return true, or if we want to match exactly, then we return true. If we don't want to match exactly, we return root dot is leaf. Is word. We matching the prefix. Right? So now look, if word equals question mark, then I have to do what? I have to go through for the kit, yeah, for n in what? In root dot words. Okay, now I have to go through the kit. Now the kit what? If search, okay, this is a search. Search what? Search anything. Search this thing will be, look, E question mark IC, right? So now I'm a question mark. I have to try each n, search each n, and then go through the go through what? I have to go through the next one. Look, there will be E. There will be a few, right? A few. And then this is the question mark, right? This is question mark. So I have to go through, try each one to see if matches this path, okay? Yeah? So how can we write it? So I have to actually use the I index. I need to go through the index. So that will be enumerate, yeah? Enumerate give us the index and the value. Index the value, right? If W equals that, and then I have to do this. I have to do the word from I plus 1, right, to the n. I want to search this one, right? So I have to search this one, yes. Okay, so I have to give a place, give a root here, right? So look, root is to say where to start, okay? If not root, then root equals self, okay? So I tell you what's happening here. So search this word, and I have to go through that, start from the next one. So it will be what? Root dot word n. Root dot word n, that's its kit, right? And then if like that, then return true. If one of it is there, if one of the paths matches, return true, otherwise return false. Okay, this is the logic here. Okay, yeah. So, okay, so let's review this a little bit. Okay, we are passing extra parameter to say where is the trie, which node to start looking for, right? Before we start with the root, with everything in the top. Now because we have this question mark, so we have the matches. Look, we have matches. If this is matches, because this matches any character, then look what happened. Look, this matches any character. IC. So I want to match IC in what? Here, right? So I want to match IC where? Here. In this level, right? Right? So this level, which one is this level? It's the next level, so I have to pass here. Right? IC. This level matches question mark. If this matches the question mark, then I go through all its kit.
Everything matches a question mark.
With question mark matches one single character, okay?
With everything.
Yeah, with one character. Let's just double check a little bit, just to make sure it's all right, okay? Yeah. So look, if this is the question mark, then we go through the root of words, okay, root of words, and then we need to go through the next character. Look, this is I plus 1 to the n, it will be this one, yeah. and then we search if the root of data, root of words A, right? Yeah, and if this root A is this one, and root of dot words A will be its kit, so it will be this one, right? Yeah. And then if that, it will return true. Okay. And okay, so yeah. Okay, so if we, I think this is it. Any questions? Any questions? I mean, this is a little bit tricky, yeah? Is it? We are using the DFS search. Yeah? Okay, so what's special about this one is here. Yeah, this bit. Okay, let me do it again. Look, previously, if we don't have this question mark, right? So we don't need to do this. Root will be self. Now we're passing this root. We are telling the search function to say where to start. Okay, so look, this is a try, right? This is a try somewhere. A try is a prefix tree, right? It's a prefix tree. Okay, so now if I'm saying, okay, the second letter is a question mark, right? It's a question mark. So you can match. Look, this first one is E. The second letter is question mark. Then I can try each pass. I can try each pass, but look, this is E question mark IC, right? Question mark IC. Then this is the second letter, right? And I want to match what? The third letter to the end, which is I plus 1, right? But where to match? I'm not matching it from the start, right? It doesn't make sense if I go back to the root. So I have to match it here. The children, the subtree of this question mark. The subtree of this question mark. Make sense? Yeah, so that's why I put the root of words n, which is here. And if one of these matches, right, this is just do a normal search. If one of these matches, and then, okay, so actually look, it could, the next one could have another question mark as well, right? If this is another question mark, what happened? Then okay, the third one is also question mark, right? Right? So what happened? Then this could be question mark again, and then I have to do this. We have to do this again. If one of them if one of them has match, is perfect match, we return true. Otherwise, we return false, right? Yeah. Okay. Okay, so that will be it. Any questions so far? What have you learned today so far?
We learned about
What's try? What's try?
try is
Why are we using the try? The tree, what does it contain?
all of the notes.
Oh.
It was, yeah.
Of the words. Okay. So I'm going to do give you a few words, and then can you build a try for me? Okay. And that'll be easy. Let's say I have a few words like Eric, Ryan, Eric, lie, Ryan, lie. Okay. Just 4 words. Okay. Can you build a tree for Daddy? Ryan, Eric, you there? Good. Yeah, that's good. Well done. Yeah. Well done. Well done. Yeah. Okay.
T.
Yeah, T means its word is true, right? Okay. Good job.
L.
Yeah.
A. I.
Well done. And then you're missing one thing. T. Yeah. Okay.
Yeah.
And Ryan. Yeah. Okay. T. Yeah. Ryan, you getting this? Ryan, you following this? Yeah. Well done. Okay. So let's say if I want to look for like Erica, Can you simulate the process of if Erica is there? Erica. So
So we got
E.
I C.
Okay, then what happened?
This is then we're still missing A, but this is the error.
Okay, yeah, that's right. We're done. Look, if we're looking for like every ERI, let's say ERI. Okay, it depending if you're looking for prefix. If you're looking for prefix, then we just return true. If you're looking for exact match, we need to check if there's a T there, right? Yeah, make sense? Yeah. If we're looking for the prefix, we don't care if there's T. If we're looking at match, exact match, we need to find if there's T. Make sense? Okay. That's it for today. Bye bye.
Bye bye.
Bye bye. Bye bye. That's it. Good job.